Hello everybody, welcome back to the online course on computer organization and architecture. We are in the module fundamentals of digital computers, and today we are going to discuss in unit 6, and this unit 6 is related to execution of program and programming languages. Okay, like as usual, now we are going to define our objective, what are the objective of this particular module, and after completion of this particular unit, we are going to achieve those particular objectives. So, the unit objective of this particular unit is, so objective 1 we have just defined is like that, illustrate the execution of program in a processor. So, this is in analysis level. That means, once you get a program, then you will be able to analyze exactly what task is performed by this particular program and how it is going to execute in a computer. Objective 2, describe the format of instruction. So, program is nothing but a set of instruction which will be executed in sequence. So, we are going to see what is the format of instruction that we are having in the instruction set of the processor. So, it is slightly in the design level, in the higher level. So, once you know the principle, then you will be able to design an instruction set for a processor. Objective 3, explain different level of programming languages. So, in the knowledge level, just we are going to give you information what are the different kind of programming language we have for computer programming. So, it is in the knowledge level, just we will give the brief idea about it. Now, in this particular module, we have discussed about the working principle of computers and the basic components of the computer. So, in the top level view of computer components are coming like that. The main component of our computer is the processor, which is your central processor unit. So, this CPU is going to perform our tasks depending on the program that we are going to execute, but the processor cannot work alone. So, we have to connect the main memory, which is the storage device, because processor works on von Neumann stored program principle. So, we have to store our program and data in the memory. So, this is the main memory component. So, here we are having the program, just we are writing as instruction, and in some memory location we have our data. So, processor works with the contents of the main memory, but how to take the information to the main memory and how we are going to get the result to the users. So, for that we need some I/O devices, input output devices. So, to control the input output devices, we have this particular I/O module. So, the main memory and I/O module will be connected to the processor through this particular system bus. Already I think in my last lecture we have mentioned that system bus is having 3 components: address bus, data bus and control bus. Now, in this particular framework, now we are going to see how we are going to execute a computer program. So, we know that while going to execute an instruction, that instruction cycle is having basically 2 phases, mainly 2 phases. One is your fetch, second one is execute. And we have seen in the fetch cycle what we are going to do. We are going to fetch the instruction from the memory and going to bring it to the processor, and once we get the instruction, now our job is to execute that particular instruction. So, we are going to execute that particular instruction inside the processor. Now, here I am giving an example of a program. So, here I have just mentioned or presented something over here in some tabular form. So, if you look into it, what you are going to get over here? Some numbers only, and along with that we are talking about memory and CPU registers. So, basically this CPU registers is a part of my processor. So, inside the processor we are having storage element, these are the registers, and it is going to take the information from this particular memory. So, it is works on stored program principle. So, if you simply look into those particular figures, I think it is difficult to understand or difficult to figure out what we are going to do. Now, we are going to see basically what does it means. Again, I want to mention that whatever numbers we are writing over here, all are in the hexadecimal notation. So, that means in base 16 system. So, here you just see that we are having that memory, we are talking about 300, 301 and 302. These are basically the location of the memory, and 1940, these are nothing but the contents of that particular memory location. So, 300, if this is in 300 in hexadecimal, Then what is the binary representation? I know that this is your 0 0 1 1 0 0 0 0 0 0 0 0. So, this is the exact address representation of the memory location, and this is basically in hexadecimal 300, but in reality in binary representation 0 0 1 1 0 0 0 0 0 0 0 0. So, it is having total 12 bits. So, the address size of this particular memory unit is your 12 bits, and we can now access those particular memory location. So, these 12 bits basically, if I am having an address bus of size 12 bit, then what is the maximum memory that we can address over here? This is your 2 to the power 12. Okay. So, that means 4 k memory location we are having. So, 2 square is equal to 4 and 2 to the 10 is your k. So, total we are having 4 k memory location. And what is the size of this particular memory location? How many bits we can store inside this particular memory location? You just see one of the content is your 1940. So, this is in hexadecimal. So, what is the binary representation? 0 0 0 1 1 0 0 1 0 1 0 0 and 0 0 0 0. So, this is the information that we have in the memory location 300 in hexadecimal. So, this is basically we are having total 16 bits. So, basically it is your 2 bytes. That means, in every memory location you can store 2 bytes of information. Now, what this 1940 represents? Now, we have to see, because by just looking into it we cannot understand anything, but if we are going to interpret it properly, then we are going to get some meaningful information. Now, here in a tabular form we are having 3 rows. Basically, these 3 rows means we are going to execute 3 instructions, and in every row we are having 2 columns. So, these 2 columns indicate basically the execution phase of this particular instruction. So, first one is the fetch phase and second one is the execution phase. Now, when we are going to look into it, then in CPU register we are having 3 registers PC, AC and IR. I think already I have mentioned about PC, which is nothing but the program counter. It is going to keep the address of the next instruction that we are going to execute. We know IR, which is your instruction register. After fetching the instruction, we are going to put it into the instruction register. Along with that, we are having one more register here, which is your AC. AC stands for accumulator. So, it is a working register where we are going to keep our information. Now, just see, now if I look into it, you just say that we are storing our instruction in memory location 300, 301 and 302. That means, we must start our execution from the memory location 300. So, in that particular case, in 300, this 300 address of the memory location we are storing in this particular program counter. Now, program counter knows which instruction we need to fetch or from which memory location we need to fetch, because if you remember this execution of fetch instruction, then what we are going to do? We are going to put the content of PC in MAR. We are not showing this MAR and MBR. Then what we are going to do? In MBR, we are going to get the contents of memory location. In this particular case, the memory location is 300, and along with that we are going to increase the value of program counter. So, PC plus 1. So, if this is my time cycle T1, this is my time cycle T2, this is my time cycle T3. Oh, sorry. So, this both will be done in T2, and in time cycle T3 what we are doing? We are transferring the information from MBR to IR. So, you just see, we are going to fetch the information. So, after fetching, what we are going to do? We are bringing this particular information, the contents of this particular memory location 300 to the processor, and we are placing it in the IR. So, this is the fetch phase is over. Now, we are fetching it. After fetching it, now what will happen? We have to increment the values of the program counter, so that we will be knowing from which memory location we are going to fetch the next instruction. So, that is why when we complete this particular fetch, that we are increasing the value of the program counter. So, now value of program counter becomes 301. So, that means we are fetching the instruction from memory location 300. After completion of the execution, we have to fetch the instruction from 301. Now, what does this instruction mean 1940? We do not know. We have to see now what exactly we are going to do. Now, it says that after performing this particular instruction, then what will happen? The 3 is loaded into this particular register accumulator. That means, we are bringing some information from our memory location to a working register, and in this particular case working register is accumulator. Now, from this particular memory location 940, we are bringing the information and keeping it into the register 300. Now, how I will be knowing that we have to bring it from memory location 940, the 3 is there and we are bringing it over here. Now, we have to bring it from 940. So, in that particular case, you just see the contents what we have in your memory 1940. So, in 1940, now we can part into 2 different parts. Okay. So, 1 and 940. So, that means this address of the memory location is available in the instruction itself. So, in the instruction, after fetching the instruction, we got the information from which we have to take the information. So, we have to take the information from memory location 940, and after bringing the instruction, what we need to do? We are going to put it into the register accumulator. That means, if I am going to see these things, what is the effect of this particular thing? So, I am going to write into the next slide, but now the effect, to know the effect, we have to know the internal organization of this particular processor also, then only we will be knowing. So, if you see that what is the CPU organization, in that particular case, so we are having this register PC, IR, MAR and MBR. Along with that, we may have some working register, maybe R0, R1, R2, R3 like that, and along with that, we are having an register called accumulator. So, this is a special register generally we say, where we are going to accumulate our result. So, that is why we are going to say it is an accumulator, and the organization that we are having over here is known as your accumulator-based processor. So, this processor is based on accumulator. Now, what is that accumulator? You just see that we are having the ALU, one of the input is coming from the accumulator and second input is coming from some, maybe from some register or maybe memory, and it is coming as a second input, and after performing the operation we are storing the result in some register Z, which is a temporary register, it is not visible to the users, and after from Z we are storing the result in accumulators. So, that means what will happen, the effect of these things is your accumulator is nothing but accumulator plus R1, maybe from register R1 we are going to take this thing. So, in accumulator based processor, what generally we used to do, we use the register accumulator to accumulate our result, and after performing any operation result will go to the accumulator. So, one of the register is implicit over here. So, that means to perform this operation I can simply write add R1. So, in that particular case what will happen, take the contents from the register R1, now add it to some numbers. To which number we are going to add? Whatever number we are having in accumulator, we are going to add this number R1 to that particular accumulator and storing the result back into the accumulator. So, this is the effect. So, we have to specify only one operand over here. So, this is your accumulator. Now, you just see what is happening over here with 0001, we are just, so in 940 we are having 0003 and we are storing it over here. So, after fetching this instruction, so 1940 we are fetching it. So, what is this particular 1940 means? It is having two parts. One part is saying this is the operation that we are going to perform, and this is going to give the operand. This is not directly operand, I can say the reference of the operand. And what we are doing over here? That means, after fetching the instruction, we come to know the address of the operand. So, we have to fetch the data from that particular operand. So, in first clock cycle, what we are going to do? We are going to do MAR is equal to address part of the IR. Now, in IR I am having this particular contents. So, this is the address part and we are going to put it into the IR, and along with that after that we will issue the read signal. So, that means we are going to read it. What we are going to get in MBR, we are going to get it from memory. So, this is in time step T1 and in time step T2 we are getting the information from the memory, and in time step T3 what we are going to do? Accumulator is equal to MBR. So, these are the 3 steps that we need to execute this particular instruction. So, what we are getting basically now? First we are fetching it. These are the 3 clock steps that we need to fetch the instruction. After fetching the instruction, we have updated the contents of this particular program register counter, and we are loading the information instruction in instruction register. When we go to the fetch execution cycle, so these are the 3 steps we are performing. First we are getting the address of my data, then we are bringing it to the MBR, and from MBR we are transferring into the accumulator. So, this is the way you can say that now accumulator is getting it over here. So, this is the way we are going to do it. So, in this particular case we are having this particular information. So, after completion of this particular instruction 1, now we are going to execute the instruction 2. So, in the similar fashion what we are doing? We are fetching the instruction from memory location 301, because this is the contents of our program counter, bringing it to the 941. Now, again it is having 2 part, 5 and 941. So, 5 is going to indicate the operation that we are going to perform, and 941 is going to give me the reference to the data or operand, what operand we are going to give. So, that means in 941 we are having this particular operand 2. Now, what is the effect? Say during execution you see what it is happening, it is showing the arrow. So, whatever we have in the accumulator, initially in accumulator we have 3. Now, whatever we are getting from the memory location 941, we are going to add it to the contents of the accumulator, and whatever result we are getting 3 plus 2 we are going to put it in 5. So, that means you can say that initially my accumulator is having 5. So, accumulator is having value 3. So, in memory location I am having 3 and 2, I suppose 3 and 2. Now, what this instruction is doing? It brings this particular 2 to MBR. From MBR it is going out and coming as an input to the ALU. So, now one input is 2, other input is 3. Now, in instruction register we are having the instruction which is the code is your 5941. So, this 5 indicate what operation we are going to perform. We are going to perform the contents of the accumulator and going to add the value that is bringing from this particular memory, and we are going to get this information in this particular result in temporary register 5, and from this particular temporary register we are going to transfer it to the accumulator. So, that now accumulator value becomes 5. Okay. So, now according to that what will happen? Now, the execution step of this particular instruction will also be similar. First 2 step it is similar. Once I am going to have these things, my data in the MBR, then T3 is nothing but it will be your Z equal to your accumulator plus MBR, because one of the input to the ALU is your accumulator, and second input we are transferring it from MBR to your second input. So, it is coming through this particular internal data. So, it is transferred to the internal data bus or internal bus of the processor, and from bus it is coming to this thing. So, this result we are storing in this particular temporary register, because directly I cannot give it to this particular bus to transfer it to the accumulator, because then there will be a data conflict. Already I am having an input data, along with that I cannot give the output data to the bus. So, there will be a conflict of data. So, in T3 we are going to have Z equal to AC plus MBR, and T4 what we are going to do? We are going to transfer the information from Z to AC. So, to execute this particular second instruction, now we need 4 clock cycle. First 2 will come as it is, and third and fourth will come like that. Z is equal to SC plus MBR and SC is equal to Z. So, this is the completion of the second instruction. Now, after completion of the second instruction, now we have to go for the next instruction. The program counter is having 3002, that means we have to fetch the instruction from 3002. We are fetching it, we are getting 2941. So, this is the contents of my instruction register. So, after fetching, we will go to the execution phase. So, what is the contents of now PC? It is 3003. Now, we are updating the values of the program counter, so that next instruction can be fetched from memory location 3003. Now, what this instruction is doing, that 2941. So, again in 2941, 941 is the address reference of my operand and 2 is the operation. Now, what operation we are performing with respect to this particular 2? You just see whatever value we have in the accumulator, we are transferring it back to the memory location 941. So, before execution of this particular instruction, contents of the memory location 941 is your 0002, but after completion of the instruction it is becoming 5. So, this is the way we are going to execute our instruction. So, now you just see what we are doing. First, we are getting one data and putting it in our accumulator. In second instruction, we are taking the one more data and adding it to the contents of the accumulator and stored back the result in the accumulator. And in your third instruction, what we are doing? We are storing the information from accumulator to this particular memory location. So, for this one also you can say that first we are executing it. We have first we are fetching it. These are the 3 clock steps. This is required to fetch it. Now, what will be the execution phase now over here? Now, that first step is your MAR. So, for execution of the third instruction, I can say that I am going to put the information into the MAR address. Basically, this is basically address part of the IR. This is the IR, this is the address part. We are putting it MAR. Now, we are identifying this particular memory location. Now, what we need to do in second clock step, we are having some value in your accumulator. So, from accumulator, we are going to bring it to the MBR and we are going to give the right signal. So, when we are going to give the right signal, then what will happen? Whatever value we are having in the MBR, that will be written in this particular memory location with this particular address. So, this value will become now 5. So, this is the execution phase of this particular instruction. So, you just see now we are having some numbers. Now, if you can properly interpret it, then we can get the effect what exactly we are doing. And to get the effect, at least we must know some internal details of the processor also. So, by looking into this particular scenario, we have just said that this may be the probable organization of the processor. It is a accumulator based processor, and in that particular processor we can carry out this particular instruction. Now, in this particular example, now what we have seen that psi address bus is your of 12 bits. So, we can go up to 2 to the power 12 memory location, which is your 4K memory location. What is the size of data bus? The size of data bus is your 16 bit. So, we are going to work with 16 bit of information. So, whatever information we are getting 16 bit, now how we are going to interpret it if it is an instruction. Already we have seen that my instruction is having a 16 bit of information. So, we are dividing into 2 parts. This is your 4 bit and this is your 12 bit, total 16 bit. So, these 4 bits are going to indicate my operation, what operation we are going to perform, and this 12 bits is going to give me the address of the operand. And secondly, this is a accumulator based processor. So, we need to specify only one operand. Second operand is your implicit. Now, in this particular example, what are the operation we have done? 1, 5 and 2. That means, opcode is 1, opcode is 5 and opcode is 2. That means in 5 this is basically read from memory, second one is addition operation. So, what is the addition operation basically we are doing? Basically we are performing add m, where m is a memory location. So, we are giving the address of a memory location. We are going to take the information from that particular memory location and we are going to add it to accumulators and going to store the result in accumulator. So, effect is your accumulator is equal to accumulator plus contents of this particular memory location. So, the second operand is my implicit reference. We need not to mention it categorically, always we are going to take the operand from one operand from accumulator and second operand from the reference we are giving along with this particular instruction. So, for this particular processor to interpret the information, that instruction, we must know the instruction format, and by looking into the scenario we have come up with this particular instruction format. And the opcode 2 is basically nothing but we can say that this is your write operation. So, we are going to write or store something to some memory or some location. So, this is read from memory, or we can say read or maybe loading something from memory to the processor. So, generally we use the term load also. So, one instruction is load, another instruction is store, and along with that we are having an arithmetic operation instruction which is going to use the ALU. Just see, in first and third instruction we are not using the ALU, because this is simply bringing the data or storing the data, but in the second instruction we are using the ALU, where we are performing an addition operation. Now, this information we are getting it that now we have to perform the addition operation by looking into this particular code 5. So, here we are having that opcode. So, instruction register we are having the opcode. So, once we are getting this particular opcode, that will be given to the control unit, and control unit is going to generate those particular control signal and it will go to the appropriate location. Now, one of the things will come here as an ALU as an add, that control unit will generate this particular add signal, then whatever input we are having in this ALU, it will perform the addition operation and store it in this particular temporary register set. Now, again I am showing this particular slide. Now, I think after knowing the details how to interpret this particular information, what is the processor organization. So, after knowing all those things, now very well now we can interpret this information and we know what are the things that we are performing inside the processor. Now, this information now we are going to give some meaning. So, we are executing 3 instructions 1940, 5941 and 2941. So, in that particular case the instruction 1940, we can say that it is having two parts, one is your operation part and second one is the address part or reference part. So, this is 1940, the operation code is 1, along with that we are giving some reference address. 5941 operation code is your 50101 and this is your address, and 2941 in case of operation it is 20010 and this is the address 941. Now, I am giving some symbolic name to that. Here I am saying that it is load M, that means load the accumulator from memory location M, add M and store M. So, we are designing 3 instructions, or say we are having 3 instructions in this particular processor. One of the instruction is load M. So, what it says? Load the contents from the memory location M and store the result in accumulator. So, it is loading some values to the accumulator. Second one is we are saying that add M. So, what it does basically? So, take the information from memory location M, add this to the contents of the accumulator and store the result back into the accumulator. So, this is the effect. So, this is opcode is 5. And what is STAM? Store M. It is basically store the value of accumulator to the memory location M. So, we are having some value in the register accumulator inside the processor, and we are going to store this information to some specified memory location M, which will be given as an input in the instruction itself. So, it is having the format opcode and memory reference. So, this is the way that we are going to interpret our instruction. So, here we are going to say that this is some code we are giving, and we are going to say this is the assembly level code, and these are the instruction which is combination of zeros and 1. We will say this is the basically machine level instruction, machine understand only this particular bit pattern zeros and 1 and nothing else. Now, finally, what we are going to get, say basic operation what we are going to do, say y is equal to x plus y, because we are going to add two numbers 3 plus 2 and we are going to get results. So, when we are going to write a program in high level language, maybe if you are accustomed with C or some other high level language, generally we used to define some variables, and these variables are placeholder, they can keep or store some values. So, in that particular case in high level language we are going to write y is equal to x plus y. So, basically what will happen, we are taking the information from memory location 940, taking the information from memory location 941, adding them together and storing the information in memory location 941. That is why you are saying y is equal to x plus y. This is the operation we are going to perform, and high level we are going to write in this particular way. Now, to perform this particular addition operation, when we are going to execute in this particular processor, we need 3 instructions. Say we are going to perform one operation in the high level, this is my requirement, but while I am going to execute, convert this particular program for the processor, we have to use 3 instructions, add x, LDA x, add y and STA y. Okay. So, these are the 3 instructions that we are going to execute. So, if we are writing in this particular code, generally say these are the assembly code, or we say this is the assembly level program, and we say this is the high level program. Now, again you just see that when I am talking about LDA x, add y and store y, we have seen that the number of steps required. So, in fetch we need 3 steps, in your execution somewhere you need 3 steps, somewhere you need 4 steps and somewhere you need 2 steps only. So, to execute those particular program, if you see that first one is going to take 3 clock cycle plus 3 clock cycle, second one is going to take 3 clock cycle for fetch and 4 clock cycle for execute, and third instruction is going to take 3 clock cycle for fetch and 2 clock cycle for execution, because it works in a continuous running clock and it is having some predefined frequency depending on the processor. So, you just see that now if you are having a computer and you said that your computer works on say 2 gigahertz. Okay. So, this is the operating frequency. Now, you will able to find out what is the time required to perform this particular operation. You just see we need total 6, 7 and 5, total 18 clock steps. So, total time required will be your 18 into 1 upon 2 to the power 10 to the power 9. 2 gigahertz is your, if frequency is your 2 gigahertz, then this clock pulse is your 1 upon frequency. So, this many times we are going to have, this is nothing but 18 into 0.5 into 10 to the power minus 9. 18 5 is 90. So, 19 into 9 into 10 to the power minus 9. That means 9. What will be the unit? Second, then millisecond, microsecond, nanosecond. 10 to the power minus 9 is your nanosecond. So, if processor is going to work in 2 gigahertz, then we need 9 nanosecond to carry out this particular operation. So, this is the way we will be knowing what is the time required to execute a particular instruction in the processor. Now, already I have said, now if this is the instruction format, that total we are having 16 bits of information to represent one instruction. Out of that 4 bit will go for the opcode and 12 bit will go for the address part. So, in that particular case, what is the total number of instruction that we can design? This is your 2 to the power 4 equal to 16. That means, we can design 16 different instruction. And what is the address space? That how many memory location we can refer in this particular processor? this is your 2 to the power 12, which is your 4096, which is nothing but 4K. So, 4K memory location we can refer. In every memory location we are having 2 bytes of information, this is nothing but 16 bits. Okay. So, this is the information that we are having. So, memory space is your 4K memory location. In every memory location we can give 2 bytes of information, and total number of instruction that we will be able to design for this processor is your 16. So, since we can design 16 different instructions, so we are having 16 opcode. So, these opcode will vary from 0 to F. So, 0 means binary representation is all 0 and F means binary representation is all 1. So, like that 0, 1, 2, 3 like that up to F we can design. So, now currently we have discussed about 3 instructions, a load accumulator, store accumulator, load accumulator from memory, store accumulator to memory, and add accumulator or add memory to the accumulator. So, these are the 3 instructions we have designed, and the code assigned is 1, 2 and 5. Other codes are now still available to me. So, now we can design some more instruction. So, now we are saying that already we have designed these 3 instructions. Now, we are saying that we are designing one more instruction called sub m. So, it means subtraction. So, what is this instruction? This is basically nothing but accumulator is equal to accumulator minus contents of the memory. Okay. We are going to give the instruction format is same, whatever we are going to design for all the instruction, it is going to follow this particular pattern. Okay. So, now along with these 3 I am going to use one more code. This is code 4, which is your subtraction 4. Like that we can now add more and more instruction. Now, along with that, now again I am going to give designing 4 more instruction. This is a similar instruction load, store, sub and m, but my reference is different. Initially we are talking about the memory, now we are talking about the registers. So, now what will happen, whatever operation we are having, say here I am going to say that this is again say load operation, this is your 1 is your 0 0 0 1, what is your 9 1 0 0 1. That means for load I am retaining this particular 0 0 1, but with that most significant bit 0 is going to say that it is a memory reference and 1 will indicate that it is a register reference. So, when it is 9, then I can give the reference of the memory. So, in that particular case generally already I have mentioned that number of registers is limited, very less number of registers. So, if I am having say only 8 registers that we are going to use, say R0, R1 to R7, so these are the register, then what will happen? In that particular case we do not require the 12 bits. So, these are basically do not care, but I can keep all those things is 0, and along with that here I am going to give the register number. So, if I say that this is your 9000 means it is going to refer to this particular register R0, the value of the register R0 will be loaded to the accumulator. So, similarly, if my opcode is your 9001, it is going to say that take the value of the register R1 and bring it to the accumulator. So, if you see the organization, we are saying that we are having some general purpose register. Now, we are having R0 R1 like that, we are saying 8 different register. So, contents of this register can be taken out from this register and put it to the accumulator with the help of this instruction 9000. So, it is referring to the register 0, and what is the opcode says, take this information and bring it to this accumulator. So, like that we can have the effect of those particular instruction. Now, if now I am going to write say this is your 5 is your 0 1 0 1, and what is your these things, when I am going to refer it, this is your 1 1 0 1. Okay. So, now if my instruction is like that, this is your opcode is your D and say it is your 0 0 say 7. Now, what basically it does? It is an addition of R. So, this instruction is basically nothing but accumulator is equal to accumulator plus R7. We are referring this particular register 7 R7. So, effect of this instruction is like that. So, similarly, you can now interpret that also. So, We are having similar instruction, one is referring to the memory location and second one is referring to the register. Okay. So, in this particular case you just see that how many different kind of combination you are going to have. We are going to have only 8 different combination, because that register's values can go from 0 to 7, total 8. So, for all those instructions we are going to get 8 different variation, maybe load R0, load R1 like that. But what will happen in this particular case when I am going to talk about LDA M? So, M is going to take all the 12 bits address. So, this is your 2 to the power 12, that means 4096 memory space. So, that means we are going to have 4096 variation of this particular LDA M, because we can get or we can give any memory location to take our information. But for LDA R, we are going to get 8 variation only, because we are having 8 general purpose register. So, similarly, load R, store R, subs R, add R. Now, you just see that 4 plus 4 we have designed 8 instructions, still we can design 8 more instructions. Now, in that particular case, we are designing some more instruction over here. So, this is INR is basically increment and this is your decrement. So, what will happen? We are having one increment operation and one decrement operation. We can increment the value of my register or memory, or we can decrement the value of my memory or register. So, in that particular case, say if I am going to say 6900. So, in that particular case, what will happen? 6 is my decrement. So, whatever value we have in the memory location 900, say if this is my memory, and in my memory location 900, say we are having say 15, then what will happen? It will decrement the value of this particular memory location, and after execution we are going to get 14. Similarly, if I am going to have say B002, now what will happen? It is basically nothing but we are having the register R2, the value of register R2 is nothing but R2 minus 1. Okay. So, this is the way we can look into it. Now, when we are using increment and decrement operation in processor, generally we are not going to use the ALU for such type of organization, because here we are having some values in the accumulator. If I am going to use accumulator for decrement it, then we have to bring it from the register to the accumulator. So, it will get disturbed, that means temporarily we have to store the value of accumulator. So, instead of doing it, what generally we used to do? We are going to put specialized circuit over here, which is going to increment it or decrement it. One simple way you can think about that how to implement it, maybe we can use a counter, which is an up down counter, because already we have discussed up down counter. So, we put the value. Once we going to execute a increment instruction, what we are going to do? We are going to count up, and when we are going to implement a decrement operation, we are going to count down. So, that means value of R1 will be placed to counter. So, basically what we are going to do, when we are going to have these things say decrement your R2, then what will happen? We may use a counter over here. So, value of R2 will be loaded over here, then we are going to count down operation, then B is your increment. So, we are going to count up, then value of counter will be incremented by 1 and going to store it back to register R0. So, like that, now we say that out of 16 we have now consumed 12 operations, still 4 are remaining left. Till now we have designed this particular 12 instructions, still 4 more codes are remaining left, 0, 8, 7 and F. So, that means we can design 4 more instructions. Now, just see what we are designing. Now, here I am saying that opcode 0 is your JMP, it is a jump instruction. 8 is your halt instruction, that means it is going to say that halting the program or stopping the program execution. That means at the end of the program we have to give this halt instruction just to say that now stop execution, need not to fetch any more information. Similarly, 7 is given as your JZ and F is your J and Z. This is JZ is your jump on 0, and J and Z is your jump on not 0, and this is JMP is your jump. So, these are the control instruction we are defining. This jump is your unconditional jump. Without any condition, we are going from one memory location to another memory location. But jump Z and jump not Z and Z, jump 0 and not 0, these are conditional jump instruction. It depends on some condition, and we are going to jump to some other memory location. So, basically what will happen, we are talking about the 0. Now, how we are going to take a decision? You know that we are having an Z flag, which is basically 0 flag. Now, when we are going to set this particular 0 flag? When the ALU operation is 0. Okay. Now, you just see that in your high level language, sometimes you write if A equal to 0, do something, otherwise do something else. So, if we are having such type of program, so in memory what will happen, we are storing our program like that. Here said this is the conditional instruction, and this is one part and this is the other part. So, I can say this is if part, this is else part. So, in that particular case what will happen? First we are going to check this particular condition. Depending on the condition, if it is true, we are going to execute this particular set of instruction, and if it is false, then we are going to execute the other set of instruction. So, it is we are making a choice. Now, how we are going to making a choice? Depending on the condition. So, such type of condition can be implemented with the help of this conditional jump instruction. So, one of the things is we are talking about jump 0. So, that means we are having this particular 0 flag. 0 flag will be set to 1 if the result of ALU operation is 0. Result of okay. So, we perform an ALU operation. If the result of ALU operation is coming as 0, then it is going to take a decision, and it may come to this particular memory location. Okay. We have to specify the memory location along with the instruction. So, we know the format. So, basically this is your opcode code, and this is address. So, what will happen? Here I am going to say that opcode is 7 and address is 350. So, in that particular case, when I am going to execute these things, if this condition is true, we are going to jump to the memory location 350 and say here it is now we are in say 320. So, next instruction should be we need to fetch from 321, but when this condition satisfies, then we are not fetching it from 321, but we are going to fetching it from 350. Similarly, that opcode 0, it is an unconditional jump. So, whatever address we provide, it will simply go to that particular memory location. Then how we are going to get it? That means we are going to load the program counter with this particular value. Then only we will be knowing that next instruction we have to fetch from that particular memory location. And it is halt, it is going to say that stop the execution of the program. So, we need not to fetch any more information from the memory. Okay. Now, you just see that we are having 16 different operation with, and we are assigning this particular 16 different operation to those particular code, 16 code. Now, when we have fetched it, then what will happen? It will come to the IR, and in IR this is the basically code, and this is the other 12 bits is reference. This code, what this 4 bit, we are going to give it to the control unit, and according to the nature of those particular instruction, now control unit will generate the appropriate control signal, and these will go to the appropriate component inside the processor. So, this is the way we can see how we are going to execute this particular program. Now, you just see that taking a small example, as I am saying that you have to write a program to calculate the total marks scored by a student in an examination having 6 subjects. So, say in your semester you are having 6 subjects, you scored marks in the 6 subject, and finally you can add them together and find out what is the total marks that you have scored. So, in some high level language you can write such type of program code. What is that? Now, we need some placeholder. So, we are defining one t underscore m. This is going to say what is the total mark. Initially this value is 0, n underscore s number of subject. Now, we are talking about the 6 subject, and we are having marks of 6 different subjects. So, we are saying m 6. So, in high level you know that we can define array. So, we are defining array. So, we are having 6 element, okay, 1, 2, 3, 4, 5, 6. So, here I am having some marks like that 25, 97, something like that. So, these marks, when we are defining arrays, so these marks will be stored in our memory in 6 consecutive memory location. Now, what we are doing? Now, what I am going to do, T m is equal to T m plus m n s. So, if this is 1, 2, 3, 4, 5, 6 location of these things, first I am going to add the contents these things to total marks. So, total marks will become 0 plus something, then we are decrementing n s by 1, n s minus 1. So, now n s become 5. So, I am going to perform this particular operation while n s is greater than 0. So, after that I am going to check, now it is 5, not it is still greater than 0. So, we will go back and we add the next number, we will decrement it like that. When it becomes, we will come out from the loop and it will go to the next instruction. So, I am getting, after coming out from this loop, what we are getting? We are adding all those numbers and the result is available in the T m. T m is equal to T m plus this array element, and these arrays will be stored in consecutive memory location in my main memory. Now, this is a high level language. Now, when we are going to write a program, so in low level or assembly level I can say like that. So, this is basically related to this particular example. Here we are saying what first I am writing, load accumulator m 1. So, basically what I am thinking, so this is the memory and we are having some memory location. In this memory location we are storing that number of subject, then I am having say 6 marks in some consecutive memory location. Okay. This is say 75, 67, 85, 92, 78, 89. So, this is the number of subjects. Say here basically we are storing 6. So, initially first I am bringing it this particular number 6, then store accumulator R 1. We are storing this particular thing in register R 1. So, now in R 1 what we are having? 6. This is the number of subjects. Then load accumulator memory. So, I am now going to give the address of this particular memory location in this particular instruction, and we are getting this list. Now, what we are having? This information is in accumulator now. So, in accumulator we are having 75. Already we are taken care of the first number. So, we are decrementing R 1. Now, value of R 1 become now 5, because already we have taken care of one number. Then what we are doing? Add m. What add m will do? It will take the contents of this particular memory location 67, adding with the accumulator and store the result in accumulator. So, we are taken care of the second number. So, we are decrementing R 1. So, now R 1 will become 4. We will say if jump not equal to 0, then go back to this particular memory location and fetch this operation. So, it will be in this particular loop till we are going to exhaust this particular 6 number. Once it is over, then say store accumulator m 2. I can say that the result we are going to store in some memory location, and after getting the result in the memory location, now we halt it. So, this is the way we are going to do it. Now, this program cannot be written for the processor that we are discussing and for the instruction set we are having, because here you just see that here I am talking about that add m. We are talking on memory location. When we go back into the next time, we have to go to the next memory location, but here in this instruction set we do not have any provision to manipulate this particular address m. So, that is why this program cannot be executed in this particular processor. If we are going to write this particular program, what will happen? It is going to add this particular 75 6 times, because we do not have any provision to manipulate this particular address M. We do not have any instruction. So, address manipulation is not available in this particular instruction set. So, if we are going to execute this particular program in this particular processor, we are going to add up 75 in 6 times. Okay. So, result will be your 75 into 6, because we do not have an instruction to manipulate this particular address M, because say if I am storing it in say 700, second one I have to take it from 701, then 702. That means, we need to increase this particular M after adding that particular number, but in my instruction set I do not have any such provision. Whatever we are doing incrementing and decrementing, it is going to increment and decrement the contents of the memory location. It is not going to manipulate the address. So, we need some more instruction to manipulate the address also. So, we will see in our subsequent lecture, but in this processor we cannot design it, because we are having 16 code and we have exhaust all the 16 code. So, we need more bits to design more number of instructions. So, one simple program I can write for this particular machine. So, load accumulator M1. So, first number I am getting it in memory location, the way I am saying that 700. So, that means load it from this particular memory location. M2, take the number from the second location, add it and store it in memory location. Like that, add M3, M4, add M5, add M6, then store the result in M7 and hold. So, we are going to write individual instruction for each and every number. So, for 6 subject it is fine, but if I say that going to add 1000 numbers, then we cannot write 1000 instructions, somewhere we have to use such type of loop only. So, for that we need instruction to manipulating address also. Now, finally, I can say that now what we are saying that these numbers we are storing in memory location 701, 702 like that. So, in assembly level we are writing it, then in machine level we are going to have this particular effect. Okay. So, now you just see that we are talking about the assembly level, machine level, and like that we can have high level also. So, here I can write that high level program the way I am writing over here. So, this is the high level program. So, the same programs I can say this is the assembly level and this is the machine level. Now, when I am going to write a high level program, now how I am going to execute it. So, somehow I have to convert it to the machine level program. So, for that we are having a software which is known as your compiler. So, compiler is there. So, we are going to compile it, and after compilation we are going to get such type of machine level code, and this machine level code will be executed in program. So, if you are accustomed with your C program, so if you have written any C program and say if you are working with the Unix system or Linux system, generally you use some compiler GCC and like that. So, if you are writing a program called say abc.set C, then what will happen? Generally you compile something like that GCC abc.say, and it is going to give me a.out. So, this is the executable file, and this executable file is not having such type of machine level code only. Now, we can execute this particular code. So, high level language can be converted to the machine level code. Similarly, we are having an assembler also. We can write the code in the assembly level, and with the help of assembler we can convert it to the machine level code. Finally, we need this particular machine level code to execute in the computer. So, assembler is going to convert the assembly code to the machine code, and compiler is going to convert the high level language to the machine code of a particular machine. Along with that, we are having another term which is known as your interpreter. So, again interpreter is used for high level language. So, in case of compiler, we are going to compile the whole program and going to get an executable file and going to execute this particular file. But in case of interpreter, it is going to interpret the instruction by instruction, and it is going to first interpret the instruction first, then going to execute it, then it will interpret the instruction 2 and going to execute it. So, if I am writing a high level program, it is going to interpret the instruction by instruction and execute it one by one. Now, finally, we are going to get this particular machine level code. Now, we have to execute it. Now, how you are going to execute it? Generally, you give the command like that a.out. What will happen when I am giving the command a.out? It will load this particular program to main memory. So, you just see that we are loading this particular program say from main memory location 150 to 157. So, we are loading it, and memory location, that means in memory location 150 I am having 1701, in 151 I am having 5702, like that 157 we are having 8000, 8000. These other bits are immaterial because 8 is the whole function. So, we are loading it to the memory location, and when we load it to the memory location, then we are having the program counter. That program counter will be loaded with the value 150, because we must know the address of an instruction. Since this program is loaded from memory location 150 to 157, so program counter will be loaded with this particular value 150. Now, we are going to fetch the instruction from 150, we will execute it. After execution of first instruction, next instruction we are going to fetch it from the 151, we will execute it. Like that, when we fetch the instruction from 157, we halt the program, we stop the program execution. That means, we are not going to fetch any more instruction from 158 memory location, it will stop it. So, this is the way we are going to execute our program in our computer. Now, sir, I feel that now you are having an idea how a program is executed in a computer, whether we are writing it in a high level language or assembly level language or machine level language. So, now just I am giving some very simple test item. Here I am saying that first question is why there are 3 levels of programming language. Now, I am talking about the machine level, assembly level and compiler. You just see, if I am going to give you the processor and just saying that you just program it, then what will happen? You have to write everything in machine level. That means, you must remember the code of each and every instruction, which is not possible, always you have to take a reference. But instead of remembering instruction numbers, slightly it is easy to remember some code like that add, subtract, multiply, load, store. So, for that what will happen? We are giving a code to each and every instruction, which is known as your mnemonics code. Now, once we have the mnemonic codes, now we can use this code to write our program. So, if we write our program with the help of mnemonics code, then we are going to say this is the assembly level code. After writing it the assembly level code, with the help of assembler, we are going to convert it to the machine code, and that machine code will be executed. But again, remembering the assembly code or mnemonics is not that easy, because now it is I am talking about the 16 instruction, but if I am going to design an processor where the size of the instruction is say 8 bit that opcode, then I can design 256 different instructions. So, remembering the different instruction mnemonics is difficult. So, for that we are coming up with a high level language. You write your program the way you think, but we have to follow the syntax of a particular programming language. So, when we are going to write C program, we must follow the syntax of the C program. Once we write it, then we can compile it to the machine level. So, this is the requirement of the high level language, because it is difficult to code in machine level, it is again slightly difficult to code in assembly level also, because you have to remember many more things. So, that is why you write in high level, then convert it to the machine code. Question 2, what is assembler and compiler, and what is an interpreter? So, already I have mentioned it, what we used to do with assembler and compiler, and what is an interpreter. Question 3, why it is not possible to implement a loop with the given instruction set of the processor discussed in this lecture. So, we are just discussing a very small processor, instruction is 4 bit. Already I have explained why you cannot implement a loop. So, for implementing the loop, we have to have some instruction to manipulate the address even, if we are going to take the information from our memory. So, this is required. So, that is why here it is not possible. Now, this unit is the last unit of this particular module, fundamental of digital computers. So, that means we are coming to end of this particular module. So, in this particular module, we have divided this module into 6 units. So, in first unit, we are talking about model of computers and working principle. So, we have discussed about how we are going to model a computer and how the computer works. Unit 2 is about digital logic building blocks, because we are going to construct a digital computer. So, we are going to take help of many more digital building blocks. So, just we are giving a brief ideas about those particular digital building blocks, and we are going to use those building blocks. So, we are not discussing anything about the design issues of those particular digital building blocks. In knowledge level, we have discussed it. Unit 3 basically deals with information representation and number system. Okay. So, how to represent numbers, integer and real we have discussed, how to represent other information like that, how we are going to write your name, store your name in a computer. All those things we have discussed in Unit 3. Unit 4 is basic element of the processor. So, we have discussed about what are the basic elements that we have in the processor in very top level. Then Unit 5 we have discussed about storage and I/O interfaces, because processor works on von Neumann stored program principle. Somehow we have to give the information to the processor. So, that is why we have to interface or connect storage unit and as well as I/O unit. And Unit 6, that last unit that today we have covered, we have discussed about how we are going to execute a program and what are the different levels of programming languages. Now, so what idea till now we have? This is a top level view of our computer. So, main element is the processor. It works on von Neumann stored program principle. So, we have the main memory, then processor is going to work with the contents available to the main memory, but how we are going to bring the information to the main memory? For that we need input output device that will be connected through I/O modules, and all those components are connected through this particular system bus. So, we are having this idea till now. So, in first module we have just have a very top level view of our computer. Now, in subsequent module, so we are going to discuss about the design of those particular processors. So, we will having modules to discuss about the design issues of this particular processor or CPU. So, we are going to discuss in details in subsequent module how we are going to design a processor, how we are going to design an instruction for that particular processor, how we are going to interpret those particular instructions. So, all organizational and architectural issues will be discussed with respect to the designing of this particular processor. We will have one module where we are going to discuss about the memory module or memory unit. What are the components that we are having? Because here we have seen in the top level only, we have the data bus and we have the address bus. With the help of these things, we can fetch information from memory and store information in memory. So, what are the basic principle to design this particular memory? How we are going to construct a memory? We are going to design all those issues in another module or memory module. We will have one module where we are going to discuss all the design issues of the I/O module. Okay. So, we will get another module. And in this particular case, whatever we are going to discuss over here, we are going to discuss the basic things only. This is uniprocessor system. We are having one processor and we are going to work with this particular processor only. We are going to execute in this particular processor. But to enhancement of the performance, we are having some advanced topics also, advanced features also, whether something can be done in parallel or not, whether it can be done in stages or not. So, some of the advanced features to enhance the performance of the computer will be discussed in one module. Here we will discuss only in the information purpose only, in the knowledge level only. So, when we are discussing about this particular module, we have defined some objective in the module level also, because in every unit we have defined unit level objective, and we have seen that after going through that particular unit we have achieved those particular objective. Now, we have completed the complete module of fundamentals of digital computer. Let us see whether we could achieve those particular objective that we have already mentioned for this particular module. So, the objective, first objective we have mentioned like that, describe the model of computers and working principle of computer, and we have defined it in the analysis level. I think we are now having some idea of what is the model of computer and how it works. So, I think we have achieved this particular objective. The objective tip 2 we have defined it like that, preliminaries of digital building blocks. So, it is in the logic level. So, what will happen in that particular case? We are just giving the ideas of those particular building blocks and we are going to use those things. So, objective 3, describe the representation of information and number system. So, in this particular objective, I think we have made that particular objective also, because now we are having some idea about the number system and how to represent those number in computer, real numbers and integer. Along with that, how to represent the other information also. Objective 4, explain the components of processor. So, it is in the comprehension level. Now, at least now we are having an idea what are the components that we are having in processor and how it works. Objective 5, describe the interfacing mechanism of storage and I/O devices. This is also in comprehension level. So, here now we are having that we have to connect I/O devices, we have to connect storage, and I have to take information from those things. So, in comprehension level we are having some idea but in subsequent module we are going to discuss all those issues in the design level. Like for the processor also, in subsequent level we are going to discuss all those things in our design level. And objective 6, explain the execution of program in a processor and categorize the computer programming language. This is in the application level, or I can say that up to some extent we have gone up to the analysis level also. So, now at least if we get an program, we will be able to analyze that particular program. And secondly, if we know the instruction set of a processor, I think you will be able to write a assembly code for that particular processor. So, it is in application and analysis level we have achieved, and in this particular course we are not going to discuss anything about this particular objective 6. We are not going to discuss anything about the programming languages like that. All those things will be discussed in some other courses. Maybe that compiler is another course where we are going to discuss about the design of compiler. So, in this particular course we are not going to discuss anything about those particular programming languages and execution of the program. Now, when we are completing this particular module, now just look into some problems in a module level. Now, what will happen in unit level problem, you must know the concept of that particular unit, then you will be able to solve that particular problem. But when we come to the module level problem, then you must know the entire concept of this particular module, then only you will be able to solve those particular problems. So, here I am giving a question 1. It says that consider a processor having an ALU with 4 arithmetic and 4 logic operations. Okay. The size of the data bus is 8 bits. Indicate how to use a particular operation of the ALU. Construct some examples to carry out some of this ALU operation and check the carry, sign and overflow bit, because you can perform some arithmetic operation. After performing the arithmetic operation, you can see the result. In the result, you can see whether it is generating a carry, whether what is the sign, is it positive or negative, or whether it is an overflow condition. So, you just formulate some examples and try to carry out those particular examples. Again, it says that provide the circuit to set the carry, sign and overflow and 0 flags. Okay. So, we are having flag bits, carry flag, sign flag, overflow flag and Z flag. So, these flag bits will be set or reset depending on the ALU operation. Now, you come up with a circuit to set or reset those particular flags. Now, once you can able to solve those particular problem, then what will happen? We are going to meet the objective 2, 3 and 4 of this particular module. Similarly, look for the second question. It says that what are the different categories of instruction in a processor? Design an instruction set in such a way that some of the instruction are having memory indirect cycle. Indicate the format of the instruction and the tasks performed by the instruction. Now, try to write a program having loop with the help of this instruction set. So, basically just take a simple example, design the instruction set, that means what are the instructions that we are going to put. After that, come up with the format of those particular instructions like that opcode, address or whatever it may be, come up with a format. Now, once you know this particular format, now you will be able to write a program with the help of those particular instructions. Okay. Once you write the program, so maybe in the assembly level you write it, then you just convert it to the machine code of that particular processor, because you are going to assign a machine code for each and every instruction. So, if you are going to able to solve this particular problem, then what will happen? We are going to meet the objective 1, 4, 5 and 6. So, with this we are coming to the end of this particular module, fundamentals of digital computer. Hope you are having some idea now how computer works and what are the components of the computer, and in subsequent module we are going to discuss in details about all those particular components. Thank you very much.